So before I go on with the slides and get sort of into some more technical examples, I wanted to do another. Oh, I need to mic up. Sorry. No, but otherwise, you know, our vast online audience will. We're going to get complaints on Twitter. It's going to be awful. All right, so so I want to just work through another example, you know, more carefully, just fully, of something that's differentially private, and that illustrates, you know, maybe the sort of the idea behind the definition. So this is actually an old survey technique called randomized response. And I'll just work through a specific example of it. So imagine that we want to conduct a survey in this room of a relatively sensitive question. For example, did you vote leave or stay in the last referendum? Of course, in this room there actually aren't that many UK citizens, so it might not work that well. But so imagine a situation. So if I go up to people in a public setting and ask them a relatively sensitive question like that, or you know, maybe something even more sensitive, like do you own a, you know, Boris Johnson costume wig, or you know, something along these lines, they may not be comfortable answering honestly. And so an idea that was introduced actually to increase the accuracy of these types of surveys, had nothing to do explicitly with privacy initially, was this idea of randomized response. And roughly what in this simplest form, what I'll do is I'll hand you a coin, and when I ask you the question, I'll ask you to flip the coin. If a coin comes up heads, you answer the question honestly, and if the coin, or actually, you flip the coin twice. If the first coin comes up heads, you just answer the question and ignore the second coin flip. And if the coin comes up tails the first time, then the second time around, you answer the outcome of the second coin flip. So the idea is that if I imagine, you know, your input is an answer to a yes/no question, then the distribution on the distribution on your output. So you answer some random quantity, which is x with probability 1/2, and 0 with probability 1/4, and 1 with probability 1/4. Okay, so basically, if your answer is a 0, you're answering 3/4 of the time you're answering the actual answer to the question, and 1/4 of the time you're answering something else. Okay. So you can implement this with coin flips. There are various other mechanisms you can use. Back in the day, apparently this was done with a spinner that would, you know, the respondent to the question would spin it around, and the circle would be divided into 3 or 4, or I guess 2 regions of unequal size. One was answer honestly, and the other one was answer the opposite of the truth. Okay, so if we answer this way, if we sort of imagine conducting a survey this way, our input now, our data set, which we'll never actually kind of explicitly get our hands on, but the true data consists of the true answer to all the questions, right? So our data set consists of a vector of n bits. And now the output consists of a vector of n random variables. And I'll use capital letters to just emphasize the fact that even when I fix, even once for a fixed value of the honest answers to the questions, the outputs are still random. So again, our output now is a vector of n bits, and we might ask, what does it mean to satisfy for an example like this to satisfy differential privacy. So our definition was that for every possible event for all possible events in the output space, we looked at the change in probabilities between when we a particular setting of the input data and another setting where one person's answer was changed. Okay? And so we can actually explicitly do the calculation here. We can fix a particular output. Okay, let's call it y, and two neighboring inputs x and x prime that differ in one position. And let's say they differ in position I. And we can ask how the probability of this output y changes if we switch the input from x to y. Okay. So we can ask what's the probability that we get this particular output given that the input is x. And we can compare that to the probability that we get this particular output given that the input is x prime. Okay. Now, one of the nice things about this example is that the probability calculation is relatively easy to do. Right? Once I fix x1 through xn, the probability that I see a particular output is just a product of, I multiply together a bunch of numbers that are either 3/4 or 1/4. Right? So what's the probability that I see a particular output y given x? Well, it's going to be for every place where y agrees with x, that's going to contribute a probability of 3/4. Every place they differ is going to contribute a probability of 1/4. Right? So 3/4 times the number of agreements between with number of agreements with x times the 1/4 times the number of disagreements. And now I'm comparing that to a different probability, which is the probability I would have seen that same output, so whatever output I saw, if, let's say Yossi's answer was different, whatever position Yossi is, right? And so, again, I'm going to get the same type of formula, but now I'm counting the number of agreements or disagreements between y and x prime. Okay, so when you spell out the ratio this way, you notice that if x and x prime differ in only Yossi's true answer to the question, then n-1 of these terms are the same top and bottom, right? And only one of the terms can differ, right? So there's one that got switched either from 3/4 to 1/4, or from 1/4 to 3/4. Okay? So this ratio is either 3/4 over 1/4 or 1/4 over 3/4, and that is either 3 or 1/3, right? So what we see is that so the probability for any particular output, the probability can go up or down by a factor of at most 3, right? And so that extends by simple arithmetic to any set of outputs, right? So that means for any event in the output space, any set of the y's, the probability of that set can go up or down by a factor of at most 3. Okay, and so what we required for our definition of privacy was that for any two data sets x and x prime, the probability of any set of outputs go up or down by at most e to the epsilon. And so what this calculation shows, so this is either 3 or a third. And so what this calculation shows is that this particular protocol, this particular way of processing the input is sort of natural log of 3 differentially private, right? So this algorithm is epsilon differentially private. For epsilon, which is the natural log of 3, which is 1.1. Okay, so it also maybe gives us a sense of why what type of guarantee this definition provides. So if you think of the reason why surveyors came up with this technique, this dates from the 1960s, is in some sense it gives you a very clear sense of plausible deniability when you answer the question. So someone comes to me and asks me a sensitive question, have you ever committed a violent crime? Or something like that. Okay? Or something that would have been incriminating in the 1960s, have you ever had a sexual relationship with someone else of the same gender? Right? Another male. So that, in some sense, whether or not, if I answer either yes or no to that question, there's, it could be that I'm answering yes because the true answer was yes, or it could be and then I'm answering yes just because that's the way the coins came out, right? And indeed, sort of any inference you try to draw about my particular answer to the question is going to be limited by the fact that there's no, when I tell you report my answer is yes, you have no idea if that answer was yes because that was my true answer or because that's just the way the coins came out. Now, what you do know, of course, is that this factor of 3, there's a sense in which your confidence about my answer to the question could go up or down by a factor of 3, and that factor might be too much for comfort for a really sensitive question. And so one can imagine versions of this where the probabilities are not 3/4 and 1/4, but other probabilities that are much closer to a half. Okay. So in general, the version of randomized response that is epsilon differentially private is that my answer will be x with probability e to the epsilon over 1 plus e to the epsilon, and the opposite of x, being a computer scientist, I'll use logical not, right? The opposite of x with probability 1 over 1 plus e to the epsilon. Okay, and you can check that these two numbers do indeed add to 1, and their ratio is indeed bounded by e to the epsilon. Okay, so what you notice, so if you plug in epsilon equals log of 3, you get 3/4, 1/4. But in general, as epsilon goes to 0, you'll get numbers that are closer and closer to a half. And for small epsilon, this will be about 1 plus epsilon over 2, and this will be about 1 minus epsilon over 2. Okay. Now, you might wonder if this is a useful way to answer questions, like from these very noisy answers, can the surveyor get a reasonable reconstruction of the answer, the kind of thing they're after, which is the average in the population? And we'll come to that in a second. But before I jump any further forward, as Are there any questions about this? Is this clear? Yeah.
If anyone ever tested whether and how whether people cheat in spite of this protection.
So the answer is yes. People have asked this question and tried to, find out.
Try it again and ask them, did you cheat?
No. Here's how you find. So the answer depends. Okay, for this particular survey, this survey mechanism has an interesting history. The short answer is it depends a lot on exactly how you implement it. So the spinner thing, that actually doesn't work that well because people answer no matter what. And you can tell that because for example, with this mechanism, no matter what the true statistics are, you should get a number somewhere between 25% and 75% as the fraction of yeses and nos you got, right? And what you observe empirically is that if you let people control the randomization themselves, the actual, depending on what the question is, of course, the observed fraction of nos is like, 90%, right? So yeah, indeed the implementation matters. But in software, like for example, what's going on inside the Google Chrome browser is some version of this, but it's implemented in software. So in principle, you could change the code of your browser to mess with the randomization, but most people don't. Yeah.
By accident, I know the empirical literature on randomized response, and the situation is quite simple. It does not work in the general population. It works quite well in a well-educated subpopulation, but not in the general population, and not if it's really important.
Right, if you give people control over the randomization mechanism. But okay, this is not a tutorial on experimental psychology. Right, just to be clear, this is not where I want to spend my time.
Whether it works as a survey method, it perfectly illustrates what's going on in differential trials.
Yeah, it's not. I do not advocate this as a survey
in the
method.
browser before the randomized response was put on, so it's more like post-randomization, but it's a particular variant on post-randomization.
But again, the goal is to illustrate the definition, not to advocate a particular methodology. Okay, and just to give you a sense of how, so basically, there's sort of a couple of ways to think about how to use these responses. But maybe the simplest one, which is, well, I'm not sure if the simplest one is, but rather than, rather than interpreting the answers as, 1 and 0, you can, there's a way to map, 0 and 1 to some minus m and plus m, some number m, where m is about 1 over epsilon. You can figure out exactly what it's supposed to be from these probabilities, such that so you, rather than people ask, rather than interpreting the result as yes and no, interpret it as plus m or minus m, where m is a number here, okay, a fixed quantity, about 1 over epsilon. And then you can set it up so that the expectation of y, given that the true answer is 1, really is 1, and the expectation of y, given that the true answer is 0, really is 0. And now, if you add up the plus and minus m's that you had, you'll get an unbiased estimator of the thing you wanted to estimate, and its variance is going to be about 1 over epsilon times 1 over square root of n. And that's that's going to be its standard deviation. Thank you. Yeah, the variance is the square of that. Yeah. So you get an unbiased estimator, and the variance about 1 over epsilon squared n. Again, where you should replace 1 over epsilon by m, where m is this number here that you get from this calculation. I forget exactly what it is. I'm not going to. But that's an easy way to use these statistics. And yeah, you basically figure out m by solving a little system of linear equations. Okay. Any questions about that? Does that example, I don't know if the example helped clarify things or was a good use of time, but yeah.
Basically, even if it worked, it's a really bad estimate.
That is actually not the interpretation I would draw.
If you're absolutely small, your variance is going to...
Yeah, so that's actually an interesting point, right? So it comes down to the relationship between epsilon and n. So as I said, you shouldn't think of epsilon as 1 in a million. A good, maybe a reasonable for this method, maybe 1 in 5 would be reasonable, 1 over 5. In which case, your variance is going to be so then you'll start getting good answers once your n is quite a bit larger than 25. That's when the variance will be less than 1.
So you've effectively reduced your sample size by 25.
That's what randomized response does. Now, if you remember the standard deviation is the square root of that. If you remember that the noise addition method I had on the slides before, the standard deviation was about 1 over epsilon n. So that goes to 0 a lot more quickly than the square root of 1 over n. And in particular, this one is never below the kind of that sampling rate error, the kind of inherent noise, the variability due to the fact that you're not asking everybody in the population, but just the survey respondents, whereas this one does go below that. And again, which methods make sense for which context is going to vary, but the Chrome browser example I gave, the installed user base for the Chrome browser is about 1 billion people. I mean, 1 billion browsers, just fewer people, because a lot of people have a couple of copies. But that means your n is, let's call it in the hundreds of millions, in which case this is pretty small. Okay, can we, wait, where's the magic guy with the, okay, can the screen magically come down? Yeah. I love it. All right. There we go. All right, episode 5. I have a feeling we may not get to episode 6, but that's okay. As I said, I had more material than I had time to, I could plausibly have time to go through. Okay, so what I'd like to do is sort of give a sense of some of the other methods one can use to satisfy differential privacy, to design differentially private algorithms. So I'll kind of come back to that technique I was talking about before, noise addition, and just say a little more about it. So this is a slide from earlier in the talk. Remember we said if I want to release I've got some vector of some summary I want to release, I can add noise to it, and the amount of noise I'll add scales with some quantity that depends on f. And sorry, let me go back. And that quantity is, I'm going to look at, what is the maximum change in the vector of statistics I can get when I change one person's data. And I'm going to measure the change in the vector of statistics by the sum of the changes in each of the components, the sum of the absolute values of the changes in each of the components. So a nice example of that is a histogram. So imagine that I've got, my data lie in some domain D, so the domain could be complicated, but I've somehow partitioned my domain into little d disjoint bins. Okay, so for example, these could correspond to, the 50 US states, or perhaps I've broken people up by, a couple of variables of, gender and political orientation and salary. Okay, and then that would correspond to some decomposition into a bunch of disjoint bins. Okay. Now, the function I'd be interested in releasing, the sort of natural thing to look at, is the just the number of people who fall into each of these bins, right? So now I've got some function which is a vector of counts, and n sub j is just the number of people who fall into the jth bin. The global sensitivity of this vector is 1, because if I add somebody to the data set, I'll increment one of these bins. If I remove somebody from the data set, I decrement one of these bins, one of these counts. I'm sorry. Okay. So I can set, I could release this histogram by adding noise about 1 over epsilon in each count. So, an example might be something like this. This is a breakdown of, blood types in the U.S. population. Okay. So these are just more examples. So this could be, the histogram could be on a line, like just I've divided numerical values into regions, or population of 50 states, or the combinations of attributes like blood types. And basically what it allows me to get is, again, an amount of noise which does, the amount of error I'm introducing due to privacy does not increase with n. Right? So as n gets bigger, once I've got a reasonable number of people in the bins, then I'm providing accurate counts for each of the bins. And those bins where I'm not providing accurate counts correspond to bins that basically don't have anybody in them, and I want to hide the difference between a bin which is empty and a bin which has 1 person in it, or a bin which has 1 person and a bin which has 2 people in it. Okay? So this corresponds, at least philosophically, to the kind of commonly used rule of thumb when releasing, say, contingency tables, that none of the cells should have a very small number of people in it. Okay, and it turns out there are lots of more complicated functions that have very low sensitivity in this sense. Okay, so there's a histogram, but also if you think of the mean of bounded random variables or covariances of bounded random variables, you can look at, okay, these are sort of more technical examples, but there are a number of optimization problems that satisfy a condition called strong convexity that I won't define, but basically corresponds to the fact that the solution to the optimization problem isn't very sensitive to a single person's data. Okay, to a small change in the function that you're optimizing, the loss function.
If you talk about income, say, then 1 Bill Gates will kill you.
Right. So this doesn't work if you're taking the mean of unbounded variables that could be sort of arbitrarily large, like income in Bellevue, Washington. But in that case, there are a number of ways. There are a number of other things we can do that, if you want, I'll talk about. But like a simple thing in that case would be to, truncate and say, well, or top code. And I might sort of separately say, well, here's the number of people whose income is above, $5 million, and now I'll give you a separate statistic among those people whose income is below 5 million. Here's the average. There's a variation on this. Maybe the distinction isn't so important for this. Well, okay, I'll talk about it anyway. One can, instead of using the L1 norm, you can use the Euclidean norm to measure differences, the effect of f of x. And then you can still use the Laplace noise, but it's even sort of more elegant to use Gaussian noise in that case. And then you get this thing that's this like variation on the definition with the delta in it. So you get a slightly different guarantee. But again, you're adding Gaussian noise in each component, which scales linearly. So the standard deviation is roughly the sensitivity over epsilon, sometimes some term that increases only logarithmically in 1 over delta. So even for very small values of delta, this square root of log 1 over delta term is not very big. And the dominant terms are the sensitivity and epsilon. Okay. And so an example of this would be if I were asking for a bunch of counts which are not about a histogram. So the nice thing about a histogram is all the bins are disjoint. So one person affects only the count of one histogram, right? But what if I'm asking sort of for a bunch of counts for properties that are overlapping and where one person can affect an arbitrary subset of these counts? Then in what I'll get is, as measured this way, the global sensitivity will be about square root of the number of counts, and the amount of noise I'll add will be will scale with square root of the number of counts. Okay, if I use the other sensitivity calculation, I'd get linearly in the number of counts. And it turns out that this actually, I'm not going to sort of do the arithmetic, but this square root of the number of counts dependency, that exactly matches the regime where some of the attacks that I talked about in the first part of the tutorial kick in. Okay, so in full generality, this term is tight, and Cynthia may get to that in her talk. I don't know if she'll talk about the relationship with differential privacy in her talk. But, there's a sense in which this, at least in full generality, this mechanism can't be improved without exposing yourself to these membership testing attacks. Okay, I'm gonna skip. I had some other stuff to say about that, but that's all I'll say about noise addition. So noise addition is one basic technique that comes up. Another one is sort of an exponential sampling technique that I'll spend some time on. And one of the reason I want to spend some time on this is that, first of all, it's widely used, and secondly, it doesn't look like noise addition. So I want to be clear that noise addition is far from the only hammer in the toolbox. Okay. So let's look at a wrench. So there are certainly cases where noise addition simply doesn't really make sense. It doesn't really make sense to add noise to something. Like, for example, suppose I've got a discrete distribution, and what I want to know is the mode of the distribution, right? If I've got some discrete set of outputs, what does it mean to add noise to the mode, right? It's not a number. It's just it's a category like, African American or something. Or maybe I've got some complicated statistic about a network that I'd like to understand, like what subset of give me a separation of a network into two parts with very few edges going across the separation. Or maybe I'm trying to what I want to release is a classifier, something to classify something that is a good predictor of cancer risk from demographic features. So all of these things share the property that they directly adding noise to them doesn't necessarily make sense. And indeed, Frank McSherry and Kunal Talwar wrote a paper in 2007. Their motivation was auction design, but it was again a such setting where sort of just directly adding noise didn't make sense. Okay, so so we can go through. So it turns out there's something else one can do. There's another kind of really natural tool to apply here, and I'll try to explain it by an example. So imagine that our data set consists of, for each person, the set of websites visited by them today. So suppose I'm doing the study at Penn State. For each of my students, I collect which set of websites they visited. So of course, there are many set of websites out there, and they could have visited a essentially arbitrary subset of them. So now I've got, there's a range of things I care about, which are website names. And suppose that the thing I really want to know is I want to know the name of the most frequently visited website, or a most frequently, a frequently visited websites. Or maybe, in general, I might be interested in the 50 most frequently visited websites or something like that. Okay. So I can sort of set this up as an optimization problem. So I've got a bunch of website names. Each website was visited by a subset of the students. And so the kind of the score of a given website is just the number of students who visited it, the number of students who have that website in their list of visitor websites. And my goal is to output the name of a website that has large score. Okay, because I want to know which websites my students are visiting. So it turns out the following mechanism does well, and we'll be able to kind of analyze it more or less completely. And given my data set, what I'm going to do is I'm going to compute the score for each of my websites. And I'm going to get a probability distribution on website names in the following way. I'm going to assign website Y probability proportional to e to the epsilon times the number of students who visited the website. Okay? So that means that websites that were visited more often are exponentially more likely than websites that were visited less often. Okay. So sort of in kind of visually what's going on, I've got the true number of websites that were true number of visits to each website if I arrange the websites on a line. and now I'm defining some probability distribution which is sort of correlated to that true number, but is smoothed out. Okay. All right, so we'll formalize these claims in a second, but the idea why this is not a crazy thing to do is that what I'm finally going to do is I'm going to calculate this probability distribution, and I'm going to sample one website name from it and output that website name. Okay? Or another thing, I could actually sample several website names according to but let's just analyze what happens when I pick one website. So here, this is like a very loose, loose depiction. So my x-axis, I imagine the website names have been arranged on a line for me, and maybe the picture is not actually all that useful. Yeah, so the real picture should be kind of chunkier than that, right? So if I arranged my website names on a line, I'd sort of get a different number of students who visited each website. And probably, a small number of websites would have lots of visits, and lots of websites would have a few visits, something like that. Okay. And now what I'm going to do, but rather than outputting the actual most popular website, I'm going to output something which is correlated to it as follows. I'm going to assign each website probability that increases exponentially with the number of visits it received. And I'm going to get a probability distribution by sort of summing all these numbers up and dividing everywhere by that sum so that they all add to 1. And then I'll take one sample from it, and that'll be my output. Okay, another, so this looks kind of complicated. It turns out implementing this isn't as complicated as it might look. So the reason this is not an insane thing to do is that on one hand, websites with high score are really way more likely than websites with low scores. On the other hand, if I look at the effect of one person's change on these probabilities, well, if I change my data, I can change the counts of all the possible websites in principle. In the worst case, it could be that I visited all of them, and now we imagine a change of my data to a world in which I visited none, in which case all of those counts would change. But the effect I can have on the probability of any one of them is sort of multiplicatively not that big, and that's because I can only change this Q function by 1. Right? I can change all of them by 1, but the effect I can have on any one count is limited. So actually, the claim I want to make is that this mechanism is 2 epsilon differentially private, and the proof is just to explicitly look at the ratio of the probability that I would output a given website Y given the input X, and the probability that I would output a given website Y given another input, a related input X prime, one where one person's data has been changed. Okay, so this is essentially the same calculation we were doing with the randomized response thing earlier, but done more abstractly. And there are really 2 terms in this ratio. So the probability that I output Y given X is e to the epsilon times the number of people who visited Y in X, divided by some normalization factor, C of X, to get all the probabilities to add to 1. Okay? And so C of X is in the denominator, and similarly, C of X prime, when I take this ratio, C of X prime winds up in the numerator, and e to the epsilon times the score given X prime winds up in the denominator. And I can bound each of these 2 terms separately. Basically, the top term is at most e to the epsilon, and at least e to the minus epsilon, because Q changes by at most 1. And the ratio of these 2 normalization constants is also at most epsilon and at most e to the minus epsilon, because it's a sum of terms, each of which changes by a factor at most e to the epsilon. And so when you just do this arithmetic, and each of these terms changes by at most e to the epsilon, and so their product changes by at most e to the 2 epsilon. Okay. On the other hand, and we can also, maybe I won't go through this calculation, but you can also sort of argue that the thing you output will never be too far. The thing you output will be the name of a website which was either visited by either the largest number of students or something close to the largest number of students. So it'll be a very frequently visited website. And the difference between, so if we given a data set X, there's some most frequently visited website, its frequency is, let's call it octave X. And what you can argue is that whatever you output with high probability is going to have frequency, whatever that optimum was, minus some term over epsilon, and this term depends on the log of the total number of websites. So even if the number of websites is like, even if you're considering 1 million different websites, this log of the number of websites is about 15 or so, and so you're off from the true count, the true maximum count by at most whatever that 15 over epsilon. And so it scales only logarithmically with the number of websites. In contrast, if you tried to use noise addition here in the naive, straightforward way, you'd get something that scales with the square root of the number of websites, which would be much worse. So you wouldn't get, when you have lots of websites, it wouldn't be especially useful. Okay. So this is something that sort of smells very different from noise addition. Again, what we're doing is we're kind of picking, we've got some set of outcomes, and we've got this score function that tells us how desirable each outcome is, and we're selecting an outcome randomly, but in a way that's correlated to this score. So we try and get a high score. So why would we want to do this other than knowing which websites Penn State students visit? I can tell you, Facebook. Like I walk around my class, and I look at their screens during my lecture, and the answer is Facebook. That's what they are. That's what they're all visiting. This thing is actually useful kind of for very generally. So completely abstractly, I've got some set of outputs. Doesn't matter whether it's websites or maybe potential classifiers that separate people at risk of a certain behavior from others. I can have some arbitrary prior on the possible outputs that weight the ones that are a priori more likely, and then I need some score function assign a score to an output to each possible output for a data set, and the condition I need is each individual score not be too sensitive to change in one person's data. So for any neighboring data sets, the scores should be close. Okay. So an example of this might be the number of points in the data set that are, like if Y is a possible classification rule, maybe a decision tree, the score might be the number of points that are misclassified in the data set. And that score can change by at most 1 when one person's data changes. So that's an example. And so again, what I'd be doing is I'd be using this mechanism to I'd be constructing a probability distribution on classifiers and selecting a classifier with the best classifiers, where the best classifiers are way, way more likely than not so good classifiers. Okay. And there's some sort of general statement about how good this is that maybe I won't prove, but the form is the same as the statement we had before. There's some, let's say OptiveX is how well the best classifier does in the classification example. What I'll get is something that here the score that would make sense would be the number of correctly classified points. I'll get some classifier which classifies almost as many as the best possible classifier for the data set, minus some term that depends on, this sensitivity term, which is 1 in the classifier case, times some term that depends on the log of the number of different classifiers I'm considering, and this epsilon quantity. Okay. An aside is that will come up in Aaron's talk Aaron Roth's talk later in the week, is that there's a benefit to choosing your classifiers in this randomized way, which is that you avoid overfitting to the data. Okay, so what this tells you is you get a classifier which is almost as good as the one that best fits the data set you have, but it's randomized in such a way that you're essentially guaranteed that if this method produces a classifier which does well on your data, then it will actually do well on the underlying population also, on fresh examples from the population. I'm not going to go into that say more than that, but that'll come up later in another talk. Okay, so this is a sort of very general tool. It turns out that actually this sort of exponential sampling idea is very general. In fact, it's completely general. So every epsilon 0 differentially private algorithm is an example of this mechanism. And so in that sense, it's almost too general. One might think it's too general to be useful, but it's actually provides a really useful design perspective. And it was used explicitly for designing many useful differentially private algorithms. I had some other notes about this connection to other areas. Maybe before I go into that, let me go back a slide and stop and ask if there are questions or people. Okay, so I had some more comments about that, but I'll skip them. And there's maybe one other technique that's sort of useful, which is an online version of this exponential mechanism. And the online version of this exponential mechanism works by, rather than being given a set of things a priori that I want to try to find the best of, things come to me like one at a time. Okay, so there's some variant of this exponential sampling technique that allows me to add to find items with large score in a sequence that's coming to me one item at a time. In order for that to make sort of sense, what is it? It's hard to maximize before you know what the maximum is going to be. So the kind of natural way to formulate, or a natural way to formulate it, is you're given a data set and also a threshold, some number t. And now the items you want to select among arrive one at a time. And your goal is to output the first item that has score larger than t. So again, each item has a score, but you don't know what the items are ahead of time. You just know that their scores aren't going to change too much. And what this sort of online version allows you to do is to kind of find items that are stop the algorithm whenever you hit an item which has really large score, a really good item. So for example, you might set, the way that the algorithm works is you start with your threshold, you get a noisy threshold, t tilde, that's the red dashed line. And now items come along one at a time, and each time an item comes along, you're going to add noise to its score and compare it to this the noisy threshold, the red dashed line. So the first item comes along, it's above the threshold, but you see a noisy score below the threshold, so you keep going. Next item comes along, you're still below the threshold. Next item comes along, you're below the threshold, same thing. And then you hit an item that is way above the threshold, you add a little bit of noise, you're still above the threshold, you stop and you output that item. Okay? And this sparse vector ID, what has come to be known as the sparse vector technique, is another kind of really useful building block in a lot of differentially private algorithms. And this algorithm, this whole algorithm is 2 epsilon differentially private. And if you run k copies of it, then you can output several items, and your privacy guarantees degrade gracefully as the number of items you're outputting increases.
Can you give an example or something like what you did before?
Yeah, so I was going to use the example. Give me a second. Yeah, no, I didn't prepare an example for this because the example I have is later in the talk, and it's more complicated. But let's see, what's a good simple example of where the sparse vector technique would make sense?
The reason I ask is that I don't exactly understand what the goal is.
Yeah, yeah.
Choose the best, or to choose and then mask it, or
So what you're trying,
looks like a secretary problem.
it is related to a, well, there is something of a, yeah, it is related to a secretary problem. What's a good example? Katrina or Aaron?
People are coming with, model parameters or something, and you're checking the fit, and you want to.
Ah, yeah. So actually, no, maybe that's actually something that'll come up in Aaron's talk. Now that's a great one. Okay, so suppose I've got a data set that is sensitive, and what I want to allow people to do is to I want to allow people to check to come to me with a hypothesis about the data set, and let's consider a restricted class of hypotheses of the form, here's a classifier. Does it perform well on this sensitive data set? Okay, and what the kind of question you could answer using this mechanism would be like, suppose they come with a classifier and I think its error rate is about 75%. Am I correct? Okay, and you would be able to so you're going to stop when this algorithm will allow you to say yes, you're correct, yes, you're correct, yes, correct, until someone comes along with a really wrong hypothesis, at which point you will stop and you will say, that hypothesis is wrong. Okay. The natural way to run this is in many iterations, where you don't shut down the algorithm once somebody comes along with a wrong guess. But the kind of privacy loss is going to scale with the number of incorrect guesses, and only very mildly with the number of correct guesses. So when people come to you with correct hypotheses, that'll be like when you're below the threshold, and you can say that's correct. And it's only when they come to you with a really incorrect hypothesis that you would sort of stop and restart the algorithm, and you'd pay kind of epsilon in your privacy loss. You'd get some degradation in privacy only when they come with incorrect guesses.
So what are you adding noise to?
So here, so in that case, you would be looking at the scores would be like the difference between the empirical performance of the classifier on the data set and the conjectured performance.
You only spend once to set T tilde, and that's
Right.
why it's cheap to say whatever the no outcome is. You spend every time you have to revise the yes outcome.
Yeah. Okay, so I'm not sure if that was a really convincing. I'm sorry, I should have prepared a good example.
Yeah, I mean, I guess like for any example you give, you can also use the exponential mechanism. So this is useful exactly when the exponential mechanism would have been useful, except the questions that are coming tomorrow are functions of the outcome.
Or I simply don't know what they are.
I don't know them.
Like people are coming and asking me questions about my data, and I just don't know what they are. And yeah, maybe I'll stop there. So it's sort of an online version of this. Okay. So I'm running till 5, right?
Unlike your predecessor, you don't have an out of down in the bottom right-hand corner, so
That's right.
we can't help you with your decision problem.
Yeah.
Well, no, I'm choosing. It's a coverage selection problem, right? So what I was going to talk about are a number of algorithms for answering a set of counting queries. And I think I'm gonna sort of skip this part, even though I think it's really interesting and it exhibits a lot of these techniques we've been talking about, and mathematically it's really cool, because I'll give you a flavor of sort of other places, some of the connections differential privacy has with other areas, and some of the other ways in which it's used. So I wanted to say more about that, but I won't. And I'll move on to the next part of the tutorial.
Want to do just a punchline from that section? Just because
Yeah.
bad news at the beginning of the tutorial that I kind of feel like we need some.
We need some good news.
But up to you.
Yeah, I'm trying to I had a particular flow in mind that's not going to work well. I have to think how to revise it. Yeah, let me use the board for a little bit, actually, if the man behind the screen could magically. Okay, so I'd like to spend, let me just load my notes. So a few minutes talking about, there's kind of a problem that has driven a lot of the research, both a lot of the research in differential privacy and actually a lot of the potential applications. And it's a problem we've touched on a bunch of times already in one way or another in the tutorial. And it's the question of releasing a set of counting queries. So what's our setup? We've got data which comes from some domain. So we've got n data points, and they all lie in some domain, and we don't really want to specify too much what the domain is. And we've got a set of queries that have been asked to us. And each query is going to be asking for the count for how many people satisfy some property in the data set. Okay? So in its simplest form, and we'll keep it straightforward. So a query Q is just a function that labels people with 0 and 1. And the question that is, this is how I specify my question, and the answer to the question is the number of people in the data set the true answer is the number of people in the data set that satisfy this property, so that get labeled with a 1. Right? So the answer to this query on X, I'll write it as a function, is just the proportion of people on the data set who have a 1. So this is 1 over n times the number of people who have a 1. Okay? And now what I'd like to do, so I'm given a set of queries. So a set of queries is a set of queries. It's a list of. Okay. So what kinds of queries might we consider? So this is also an input to my algorithm, are the questions that I'm being asked. And the kind of things we might want to support are sort of, well, okay, sorry, let me back up. So I should think of this set of queries as giving me a list of, I'd like to produce sort of one object, one synopsis or synthetic data set that is representative of the underlying data set with respect to all these queries. So for example, these queries could be correspond to geographic regions that are rectangles on the plane. So I want to be able, for every rectangle in the on the map of England, I want to be able to find the number of people who live in that rectangle. Okay, so that would allow me, if I can answer that question for any rectangle, by putting together rectangles, I can sort of approximate, I get a good answer for the population of roughly any natural region that's not too spread out. Or another type of set of questions I might want to be able to support is, wait, sorry, I need an eraser. There we go. The types of questions that are allowed by the on the map product that the census produces. So these give me, for example, I've got I can specify 2 regions, and I can find out how many people live in one region and work in another. Okay. And in addition, within that, I could add other features, like how many people live in this region, work in that region, and are males between the age of 35 and 45, things like that. Okay. So this is just some arbitrary set of questions that I'd like to be able to support, whose answer I'd like to be able to provide. So and the kind of thing I might want to output is either like a very simple thing I might want to output is just a list of answers to all these possible questions. Okay, so maybe I want to be able to output, y1, y2 up to ym, where the difference between yj and the actual answer to this query is at most some error tolerance, which we'll call alpha. Okay, some number alpha. Or I might want to be able to output some, so that would one answer would one format for my output would just be a list of answers. A natural thing I might want instead would be a synthetic data set. Okay, so I'll call it x tilde, such that each of the answers, the synthetic data set is representative of the true data set for this set of questions. Okay, so this actually is a kind of a goal that's explicitly formulated in a lot of the statistical disclosure literature. You're trying to formulate a synthetic data set that supports a given set of analyses. Okay, and for today, we'll just consider a very simple form of analysis that looks like this. And there's something in between these two where I could output some sort of weird data structure that allows you to answer any query you want, but it's sort of more compact than this thing, but not necessarily an actual synthetic data set. Okay, so some synopsis of the data that allows an analyst to answer these questions. Queries themselves. Actually, this type of thing actually does come up in the statistical literature sometimes too, where in the synthetic data literature, sometimes you'll produce like not a single synthetic data set, but actually a kind of a collection of synthetic data sets. And what you're expecting the analyst to do is to run their analysis on all of those synthetic data sets and somehow aggregate the results to get their final answer. So that's the kind of thing that might fall into the second category that doesn't really fall into the third. In any case, so it turns out that in terms of like how hard it is computationally to solve this problem, these things are very different. But if we just care about whether or not it's possible to solve the problem subject to differential privacy, it turns out these things are essentially equivalent. So they're very different computationally, but for what I'm going to say today, we may as well consider them to be the same. So basically, I just want to find some way of providing answers to all these queries. And based on the noise addition technique we saw, so there are sort of various algorithms that have looked at solving this problem. The first one is to add is just to sort of compute the answers to all the possible queries and add noise to each of them using, say, Gaussian noise. Okay. And there, as we saw, the alpha we can provide is something like the square root of m over epsilon. There's a dependency on delta, which we're going to ignore. Sorry, over n epsilon. Okay. And so this depends very nicely on n, but it has a very poor dependency on the total number of types of analysis. So if I want to support a very rich set of analyses using this simplistic approach, I'm going to pay a lot for it's not going to work very well because I'm going to pay a lot in noise. But this is what we get by the sort of simple noise addition technique. And it turns out one can do more sophisticated things based on this exponential mechanism and various variations on, and other ideas, I guess. One of them that works quite well and that historically was the first is I'll use this exponential sampling idea we had on the slides to select a small data set that is representative of x with respect to these queries, to my target queries. Okay. So I won't go through the details, but the idea is I'm going to use this exponential sampling method to select a synthetic data set. No, so I'm going to select a small data set. It need not be a subset of the original. What I know is that somewhere out there is a good data set, which I could find by taking a random subset of the original. And what this exponential sampling method guarantees me is I'll output something which is sort of almost as good as that data set. And I'll sort of explain how these methods relate to each other in a second. And then there's another, well, there are actually a few other categories of approaches, but another sort of category of approaches.
Wait, so what do you gain? You have to show us what you gain by doing that.
Yeah, I will. In a sec. So then there's sort of I will tell you what we gain in a second. So there's another kind of category of approaches which I'll lump under the label of learn the data set. So there what I'll do is I'll try to kind of learn a concise representation of a small, like some sort of concise representation, some sort of synthetic data set, which is representative of X, again, with respect to this given set of queries. And to make these easier to compare, it actually helps to reformulate the bounds a little bit. So if I take this this bound and reformulate it in terms of n, if say what's the n you get, what is the sort of n I need to get a given level of accuracy, what I'll get is something like square root of m over epsilon alpha. This exponential sampling idea is due to Blum, Leggett, and Roth from 2008, and it gets sort of a different relationship between these parameters. What this sort of exponential sampling idea will give you is something that has a worse dependency on the accuracy you want relative to this, but now a much, much better dependency on the number of queries. So it'll allow us to support a number of queries that grows exponentially quickly in the size of the data set, or almost exponentially quickly in the size of the data set, as opposed to only sort of quadratically in the size of the data set. And this paper was actually, so this is in 2008, it was very influential, and it really got people thinking about this problem I've discussed, and it drove a lot of the later research. But what you should notice is that there's this new term that appeared, which is the sort of size of the data universe. Okay, and really, what that term is not. In fact, there's sort of a generalization of these results. That term isn't really fundamentally about the size of the data universe. It's some measure of how complicated this set of queries is. Okay, it's related to some measure of dimension of the set of queries I want to support. So the more rich a set of analyses I get, effectively, the higher this term will become. And but it's still never it's never larger than the log of the universe size, so the number of bits it takes to write down an element of the data. So in particular, if your data can be represented reasonably, concisely, like the answers to a census on a census form, then that quantity is not too big. And then this sort of learn the data set approach, there's actually a whole pile of algorithms that kind of fall under this category, but like a representative one is based on an idea called multiplicative weights. And it gets us something more like, again, we get a logarithmic dependence on the number of data points, the number of queries you want to support, but it has an even better dependence on the number of, on the kind of the dimension, the richness of the queries, and also on the error. So that's number 2, by the way. Okay. So, so the point is simply to explain that these algorithms exist, right? So we're not going to go through them in detail, and that they demonstrate something really surprising, which is that that was surprising to me, at the time, and I think a lot of other people, is that this sort of idea of noise addition, while it's good for some problems, even for very simple problems, it's often far from the best solution. And you can, by thinking creatively about the problem, you can find much, much better solutions that have leak the same amount of information. Indeed, one can get sort of methods that generate synthetic data that will support a number of questions that grows, as I said, exponentially with the size of the data set. And that's sort of a counterpoint to some of those reconstruction attacks I talked about earlier. So I could try to explain more about the details of these algorithms, but I think I won't. What I'd like to do is take the remaining minutes I have to kind of highlight a few other places where research on data privacy has gone. and on differential privacy, I'm sorry, has gone. And maybe if the magic screen person can lower the screen again, that'd be great. Okay, so let me say that I appreciate you guys sticking this out. It's been a long day. This is our second of 2 3-hour tutorials. So we're not going to get through all of this, but I'll give you just some flavor of a few other topics where that research on differential privacy has touched on. Okay, so let me start with a little bit about local algorithms, and the reason to talk about these is because in the commercial applications of differential privacy, these have proven very important so far, and there are kind of examples of they're much more sophisticated examples of the kind of very simple randomized response survey scheme that we talked about earlier. Okay, so this has come to be known as the local model for differential privacy. So it basically, up till now, except for that randomized response example I did on the board, all the algorithms I discussed assumed that sort of all the data is piled into one place. And then it is, there's some analysis that's performed, and then the output is produced, and the analyst only ever sees the output. Okay. But that requires either a place where you can pile the data, or some kind of potentially complicated cryptographic protocol to kind of simulate a trusted data store. Okay, along the lines of what Peter was talking about earlier in the privacy-preserving record linkage. Okay, but what happens if we don't want to do that? What happens if we don't trust the aggregator to store our information correctly, and we don't necessarily have the luxury of engaging in a protocol with lots of back and forth? Okay, so an example of this is the applications both that Google and Apple have been talking about, where they're collecting information from mobile users and users of their browser about let's say websites that are visited. So we've got we've got a bunch of users that visit a bunch of different websites. They all would like to, and they're going to submit information to a central server like Google or Apple. And Google would like to be able to answer questions like, well, how many of these users are visiting the following site? Which website are they visiting? Or how is their homepage set in their browser, or something like that? Okay. So we might want to know how many people go to this website, for example. Okay. For various reasons, both Google and Apple would like to collect this information, would like to get these aggregates without ever collecting and storing the actual sensitive information. Okay. So this leads to the following model. We've got n people. Each one has a private data point, and they're going to individually, locally, kind of do something to randomize their own data, and send what they're going to send to the untrusted server is not their actual input, not their sort of true answer to the question, but some randomized version of it. Okay, and the example you should have in mind for now is that randomized response protocol we talked about earlier. Okay, and when I say randomizes this input, imagine this is done by a piece of software or hardware. It's not necessarily the user sort of flipping coins. So we don't want to necessarily force the user, put that burden on the user. It should be easy, but algorithmically, we're going to think of the randomization operator as being performed locally on the user's computer. Okay, so in order for an algorithm like this to be differentially private, it turns out it boils down to just each of the little green boxes has to satisfy that differential privacy condition, which is, for any two inputs that let's say user number 2 provides, the output probabilities Q of x and Q of x prime, those two distributions should be close. Okay. And this was actually introduced, some model equivalent to this was actually introduced well before the original paper, but under a different name. So given this sort of constraint on the setup, you can ask, well, what kinds of things can we compute in this model? Can we do as well as we could before? And what kinds of interesting things can we do? Right. So one thing we know is that we can answer simple yes/no questions with at least some reasonable amount of accuracy when n is large. What about more complicated things? Okay. And it turns out there are sort of lots of interesting things one can do in this model. And in fact, we have from the theoretical point of view, a much better understanding of this model than of the more general centralized model. And that's because just this model is so much more constrained that it's much easier to understand its limitations. Just to give you an idea of the kind of thing, sort of neat thing one can do, and that this is actually what's going on, the functionality that the Chrome browser is trying to implement. I've got a set of users. I've got a set of items that actually really do correspond to websites. Let's say there are D of them. The frequency of the item A is the number of users holding A, or the number of users kind of visiting a given website. And the kind of thing the untrusted server wants to be able to reconstruct is some kind of histogram of which websites are the most frequently visited. Okay, and like a very concrete thing that they do with the Chrome browser is try and look at how people, what websites do people use to set their homepage? What do they set their homepage to? Okay. Now, there are a billion Chrome users. There are not quite that many homepages, but lots of them. So maintaining kind of an explicit list like that would be would consume a lot of space. And so what they want is a more succinct data structure. What they want is something what they want to be able to maintain is a list of the most frequent items, the ones that, the websites that are most frequently used as homepage settings, and estimates of the frequencies of those frequent items. Okay? So, if these are the true frequencies, they don't really care about the small frequencies. That they want are approximate versions of the big frequencies. Okay, and so this is maintained as some kind of frequency, some kind of list of items and approximate frequencies. And what you want is a list that captures the most frequent items. Okay, and this has received a fair amount of study. And it turns out that one can sort of the naive ways of doing this would require an amount of space, an amount of time that is proportional to this number D, to the total number of different websites that might ever be used by people as their home pages, right? And that is kind of, way too large. But it turns out we can get away without such an onerous requirement. So let me sort of formulate the problem first. The formulation comes from a paper of Shu, Khanna, and Roth. So we want a protocol that's epsilon differentially private. The L stands for local. And we want something that approximates all the frequencies well, meaning that it captures all the very frequent items and estimates their frequencies well, and it doesn't capture any items it doesn't incorrectly think of rare items as frequent. Okay, and then the last thing we care about is sort of computational efficiency. So we'd like a protocol that runs in time, not polynomial, that runs in time, well, ideally proportional to the log of the number of possible websites. So the number of bits it takes to write down a website name, and not the number of possible websites. Yeah.
What are the news here? New ones,
sorry. V's. They got switched. So V's are the websites visited by the different users, and the boxes got cut from the picture to save space.
And F hat is
So. Yeah, I'm sorry. I'll take it more slowly. So here, for each. Okay, so what I'm maintaining are a list of frequent items and their frequencies, and implicitly, I'm all the less frequent items. I'm thinking of their frequencies as zero. I'm approximating them as absent, even though they might be there. And what I want is every single one of those estimates to be correct. Meaning, if I think of an item as infrequent, it really should be infrequent, and if I think of an item as frequent, it should be frequent, and I should have captured its frequency correctly. And so you can think of it as implicitly I've got an estimate of the frequencies of all items, and each of those implicit estimates should be correct. Not sure if that clarifies that. What I want is this sort of, well, okay, there's something missing. So I want to be, there's a probabilistic component to this. So I want, let's say, the expectation of this quantity to be small no matter what the data set is for any possible data set. And I guess I won't go into the details, but what I'll say is that one can actually kind of accomplish this. One can get protocols that do this reasonably well, and that the amount of space they use on the server scales only with the logarithm of the number of different websites I might want to consider. And there are even versions where the running time also scales like that. So I was going to try to explain how those.
They all visit equally likely.
So okay, so if it
So it doesn't depend on the nature of the data?
well, so the accuracy threshold is such that if everybody visits a different website, you're not going to be able to see that. And that's because, in some sense, if everybody visits a different website, then you can't really hope to satisfy a condition like differential privacy and learn the list of visited websites. Right, so you can only hope to see websites that occur with sufficient frequency. I'll quickly explain a solution that is very simple but slow, and then I'll sort of explain one of the ideas that goes into improving it. All right. So, for example, here's an algorithm that works. It's just it doesn't satisfy all our desiderata. It takes a lot of space and it's too slow. So what I'm going to do is I'm going to think of I've got an input, value. I've got for each person a value v sub I. Sorry, x got changed to v. And I'm going to represent it as a vector with a 1 in the position corresponding, a long vector of length d with lots of zeros and a single 1. And it'll have a 1 in the position corresponding to the website I visit and zeros everywhere else. Okay. So this requires me to write down a vector that is as long as the number of different websites I would ever consider, which of course is sort of too implausibly long, but we'll consider the thought experiment. And now what I'm going to do is use sort of randomized response to perturb that vector. And a very simple way to do that is to just add Laplace noise of magnitude 1 over epsilon in to each entry. Or in fact, what I could do is apply that coin flipping procedure that we worked through on the board earlier. I can apply that coin flipping procedure to each component of the vector. So I can flip each component with probability close to a half. And I can sort of change the representation a little bit so that it remains, so the error remains mean 0. So I get, that'll make my life easier. And then the aggregation is going to be very simple. So what the aggregator will get is it'll get a bunch of these really long noise vectors, n of them, and it's just going to take their average. And it turns out that's going to be its frequency estimate. Okay, so it's basically running D versions of that randomized response thing we were talking about earlier, but now in parallel. And it turns out that's actually, it's not that bad a thing to do, surprisingly. If you
responses.
Sorry?
If you have a billion responses.
If you have a billion responses, right? So we'll get to that in a second. So basically, you just take the average, and that is, that big long vector, that's your vector of frequency estimates. So that you're going to get a bunch of noise, a bunch of random numbers, and when you want to figure out the frequency of website number j, you just look for the jth entry in that vector. So by the same calculation we did earlier, each entry has standard deviation, square root of 1 over epsilon squared n. And so when you've got, a billion people, when you're Google and you've got a billion people to talk to, you get an error that goes to 0 very quickly. that goes to 0, that is small in each entry. Now, that means every individual frequency estimate is pretty good. There's a little bit of a multiple hypothesis testing problem going on here, which is that there are maybe there are a billion Google Chrome users, but there are actually about that many different websites out there also, right? And so, you have to take into account that they're not all going to be this good. But it turns out the worst case is not that bad. The worst case is only worse by a square root of log d factor.
This comes from the maximum of normal?
This just comes from in this case they're binomial, but yeah, this is just a union bound over d possible things. Okay, so this is what you would get. This is actually, not horrible accuracy. Again, it takes a lot of space and it's very slow. But the accuracy I get only scales logarithmically with the number of websites I care about, and goes down linear. The term inside the square root goes down linearly with the number of users I have. So that's a good scaling, right? Sorry, I had a picture. Okay.
So where's the billion coming from?
Where's a billion?
N.
N. Yeah. So a billion is the number of is the size of the installed Chrome user base.
Why do you need a billion?
Oh, you need n to be larger than log d over epsilon squared, which potentially is much smaller than a billion.
Yeah.
Right. So it turns out that this scheme, if all you care about is accuracy, this is as good as you can get in this local model. In the centralized model, you can do a lot better. You can get something that the accuracy goes as log d over epsilon n. So this is a lot larger than the error one would get if we could pool the data all in one place. But it gives us, still pretty good accuracy, and it doesn't require pooling the data. Okay. It turns out you can improve things a little bit by some kind of careful post-processing, but that's only going to improve the constant factor up front. It's not going to change the basic scaling. Okay.
You want square root in front of your far worse than centralized, right?
Sorry? No. The centralized model, you get this, which is much smaller than this. Well, okay, it's much smaller when either of these terms is less than 1, then this is the one you want. But you don't necessarily have that. So this is the one you get. All right? However, the problem is that at the scale at which Google and Apple operate, this is sort of a reasonable accuracy. However, it's not a scalable solution in the sense that it's very slow and it takes a lot of space. Mm-hmm. And it turns out that basically one can get exactly the same accuracy with much more compact reports and a much more efficient aggregation a much more efficient algorithm for the aggregator by combining a few different ideas that I'm not going to go into. So I'll just say informally what the ideas are. So there's some combination of ideas in dimension reduction, where you're sort of doing some kind of random projection onto a low-dimensional subspace, and then ideas from the data stream literature in computer science for kind of teasing apart the most frequent items that you trying to find those most frequent items efficiently in this kind of sea of things that could be frequent. And I guess I'm not going to say more than that. Okay, so I wanted to get to some connections with other areas, but I think they're going to come up in other talks, and so I'm just not going to go into that. I'll finish up with a last point, which may kind of may resonate with this audience, which has to do with sort of actually doing statistics with the output of differentially private algorithms. Okay, so this is a combination of this is both a caveat and a kind of a teaser, in the sense that I want to convince you that you can do interesting things. So maybe I'll just stick with a picture. Okay. So what's going on? So imagine we've got the following very simple question. I've got a data set of about 1,000 people, and I want to know how many are male, female, and answered yes or no to some question. Okay. So I can think of this as a histogram with 4 bins, and I can add noise to each of these counts using the algorithm we talked about earlier to get noisy counts that are roughly representative of the original counts. Okay. But so on one hand, this seems like a reasonable thing to do. Each individually, these counts aren't that far off. But it turns out that if I want to do, if I want to answer various sort of statistical questions based on them, I do have to be careful. So for example, suppose I wanted to run an independence test based on these statistics. I might get very different looking results if I treat the differentially private outputs, these noisy outputs, as if they were the real things. Okay. And
No one in this room would do that.
and so, I think this is a very natural thing to. I hope this is sort of a point that doesn't require a lot of elaboration. But basically, if I look at the kind of observed p-values for many samples from the null distribution, so if I set these things up to actually be independent, and I look at the chi-squared values I would get for the the p-values I get for a standard test of independence, they are distributed essentially uniformly the way they should be. But if I try to do the same if I try to run the same test on the noisy data, then I'll get weird answers. I'll get something that's biased. Okay. So the caveat here is that you can't if you're doing even relatively simple but careful analysis, you can't treat noisy values as if they're the real thing. On the other hand, the positive thing is because we're completely describing the process that maps the survey data to the output, you can actually explicitly take that process into account when you're designing your tests. And in fact, it turns out if you do that, you get you can fix the correction, and you get relatively little loss of power. So the fact that you've corrected things so that under the null distribution you get the right distribution on p-values means your significance will be correct, and how much loss of power you'll have depends on n and epsilon and the analysis you're doing and so forth and so forth. But the point is that this kind of thing can be done, but it just requires explicitly taking account in your model the way the data were perturbed. Okay. Again, so there's a minus and a plus. So the minus is if you treat the data naively, you'll be led to make mistakes. On the other hand, because the entire process is fully specified, the algorithm that produces the outputs is fully specified, you can explicitly fold it into likelihood functions when you do when you're doing statistical analysis, and you can actually do this kind of correction. Okay. So at this point, there are a number of papers that do this. So there's this paper of Wang-Li and Kiefer from earlier this year, and also another paper by people at Harvard, and I'm blanking on the expansion of the acronym, but basically doing something similar for a slightly different independence test. Okay, so I would say this is something that remains, not so much is known about. So we have a lot of results on sort of asymptotics and things like that about differentially private algorithms, but the best way to use them for a particular finite n and specific value of epsilon, that's often that's still well, not exactly known. And in particular, for these more complicated algorithms that we didn't really get into, but the ones that use exponential sampling and the sparse vector technique and things like that, that type of correction is much more complicated. Okay, and you know, I would say that's something that needs to be done. It's certainly not well known. Yeah.
If you don't insist on correcting the likelihood function, but you specify the full posterior distribution instead, you just feed the differential privacy formulas in because they aren't data dependent, so they always multiply the likelihood contribution, and you can simulate with any posterior simulator that you want.
Yes, so instead of sort of,
Because they
you're
don't
saying,
depend
oh,
on data.
instead of doing the correction analytically, you can do it
Because they don't
empirically.
depend on
Yes,
data,
yeah,
you
absolutely,
always do.
absolutely, right. Yeah, so, and that only, sort of computationally, all that requires is to be able to run the algorithm.
That's correct.
Which is not, which, you know, if it's an algorithm you wanted to run, hopefully you're able to run it, right? Yes, absolutely.
But I guess the noise distribution for some of the algorithms Adam was mentioning, where you're trying to learn the data set, is data dependent.
No, but actually the point is still valid. So assuming the algorithm is sufficiently efficient to run lots and lots of times, you can basically, you know, empirically approximate p-values by just running things lots of times on synthetic data from a given distribution and sort of
I believe
figure out the sampling distribution of the statistic you care about. Okay, anyway, so I'll stand by my point that the best way to do this remains, I think, not entirely clear. But the clear point is, again, because everything is there's sort of full transparency about what the algorithm is, it can actually be done. So this is, I'm making this point to contrast with a lot of traditional disclosure techniques where the exact choices are dependent on human judgment and aren't necessarily publicly known, never mind mathematically well defined, or the other way around, mathematically well defined, never mind publicly known. Yeah, and Sophie?
Yeah, do you have a reference on what you were just discussing a second ago?
Which one?
The idea of generating multiple.
I think maybe both of these papers actually do that, but I guess.
We do
Oh, that's what they're
that.
doing for their correction.
Marco, are you the G?
Yes.
Okay. Sorry. See, I felt this intense sense of guilt. Help me expand the acronym. Gabardi, Lee, Rogers, and Vedant. And I'm not even sure when I made this slide what this S15 was. That's not me, but like now I'm blanking what it was. Okay, but what? All right. So sorry about that, Marco.
So that's the technique they use in that.
They do a bit of both. They do there's an analytic version and an empirical version.
Okay, cool.
Yeah.
There's a lot of them. If you're willing to approximate posterior distributions, you can work out the first two moments directly.
Yeah. With simple noise addition, like there's nothing kind of really fundamentally complicated going on. Although of course making it work is like, you know, worth writing papers about. But with these sort of more complex algorithms, then I would guess there's probably lots of work still to be done, and the best way to sort of make good use of the outputs.
You run that stuff on your noisy data.
So we don't have enough compute power. We work out approximations that are adequate.
Okay, so I'll leave you with a question. How can I use differentially private outputs to draw conclusions about, you know, data to make meaningful inference? So algorithms with understanding the accuracy guarantees of the type that I was talking about mostly in this talk is, I think, a necessary step, but not a sufficient one. And I think there's more to be done about the various on this topic. Okay, so at this point I have comfortably exceeded my time.
That slide with the middle sentence is a great way to end the first day of this.
Right. So I'll remind you differential privacy. The basic idea is to define privacy by limiting the effect any one person's data can have on the distribution of outputs, and hence on the inferences that can be drawn. And there are lots of techniques that have been developed for doing this, but it remains a very active research area, and one that hopefully will play a role in this in the remainder of the workshop and the program. Thanks.
Can I just remind you, there's a wine reception now, or at least there was 20 minutes ago. Is it all gone? And tomorrow.